Zombie Apocalypse.
Good day, MEI students who are currently taking Electrical and Electronics Technology course. Once again, this is your course facilitator. This is Sir Kenji A. Merenciano. And surprise, I have another video as your reference for this course. Since we're having only limited time based from our schedule, July 23 is the end of mid-year. So I decided to record this video as your reference so that additional knowledge or information for you to understand and what do you call this, and appreciate the field of these two disciplines. That's why I'll be giving you an overview, a brief introduction. So since we have different types of components, I'll just give you the basic. So I'll be introducing you to last meeting, if you can still remember, the video that I presented was all about an introduction to resistors. So for the continuation, I will also present another set of components, starting from capacitors. We also have inductors, diodes, and transistor. So without further ado, I will now present you my material. Last meeting, I presented the fundamental component in electricity and electronics, which is all about resistor. So for today's meeting, we will continue the discussion on other related components used both in electricity and electronics. So what are the definition? What are its function? What are the parts? And its classification. So this time, we will continue the discussion on the selected components. The next component used in electricity and electronics, we'll talk about capacitors. I know you also encountered and learned this from previous lessons or topics and for this course. So let's get to know more about capacitor. Capacitor class is a device that stores electrical energy in an electric field. It is also a passive electronic component like resistor with two terminals. So meaning to say, class, it is also an axial lead component, meaning to say it has terminals at both ends. Since we're talking about capacitor, we have this term known as capacitance. Capacitance is the ability to store electric charge. Or in other words, it is the ratio of the amount of electric charge stored on a conductor to a difference in electric potential. We already know that resistor has a unit of measure, which is known as ohms, or a symbol known as omega. For capacitor, we have farad, or capital F as its symbol, derived from a scientist or an inventor whose name is Michael Faraday. It is the unit of electrical capacitance, or meaning to say, it is the ability of a body to store an electric charge. Capacitor also has different types, from electrolytic to polyester, ceramic, until we have trimmer and tuning capacitors. So capacitor can be classified as polar, which means to say it has a positive and negative terminal. So in connecting or installing this component, first you should know uh, the direction or the positive and negative terminal of this component. Compared to non-polar, it has no polarity. So you can adjust. There's no need to adjust or to consider the charges, the negative and positive side of the component. We also have variable capacitors, uh, wherein the good examples are trimmer and tuning capacitors. So these are the symbol as well the example of this passive component. Capacitor class is made up of two conductive plates and separated by a dielectric. Okay, so what is dielectric? So a dielectric substance, especially one used in capacitor, used to maintain an electric field between the plates. Can you look at the illustration on how electric field is maintained when there is a flow of current? When you say dielectric, it is having little or no ability to conduct electricity, generally as a result of having no electrons that are free to move. Uh, Dielectric is not a conductor of the direct electric current. A dielectric class is an insulator. A dielectric permits the passage of the lines of force associated with an electromagnetic field, but it does not conduct uh, current. So this is the illustration of the capacitor based on its symbol, which is it has a lid at both ends, and it has a conductive plate. And you will also consider the distance between the plates, or uh, on this part. This is what we call the dielectric, right? So it rather permits the passage of the force with electromagnetic field. Okay, so to get to know more, capacitance or capital C is the ratio of the amount of charge. Charge can be symbolized as Q. C is for capacitance on either conductor, the potential difference or volts between the conductors, or simply C is equals to charge over voltage. So in other words, a typical conductor comprises two conductive plates and a non-conductive dielectric material. This is what I've said before. And this material separates the two conductive plates. So applying voltage to the electrode or plates of the capacitor causes an electric field in the dielectric material. So that's how capacitor stores electrical energy by means of the two conductive plates with the help of a dielectric. So let's get to let's identify or classify the different types of capacitors. And what are they? First one is electrolytic. This is the popular or common type of capacitor. It is used when the large capacitor values are required. For its description, it is a thin metal film layer used for one electrode, and the second electrode or cathode is a semi-liquid electrolyte solution, which is either in jelly or paste is used. So that's what makes up, or what is inside in a electrolytic capacitor. Application for this component are generally in the DC power supply circuit because they are large in capacitance and small in reducing the ripple voltage, or these are what we call noise or unwanted signals. The disadvantage of this component is they have low voltage rating because of the polarity. the positive and negative of this component. So this is an example of a capacitor. So at first glance, you will notice it's a cylindrical or somewhat a barrel shape with different symbols or letters or numbers. So later we'll get to know what's the meaning behind this text, and it has a what do you call this, minus or negative symbol to present or to indicate its polarity. So one way, since this is a polarized component, meaning it has a positive and negative, to determine the positive and negative, you can see the negative or a different color of a line, okay, with a negative symbol. So this is the negative part of the electrolytic. If it has no indicator based on its covering, we can differentiate positive from negative based on the length of the LEDs or terminal. If it's short, therefore it's a negative terminal, and if it's long, it is a positive. So as I've said earlier ago, uh, capacitance is the ability to store electric charge, and the unit of capacitance is measured in farad or capital F. So here, if you can still also remember, I presented the different what do you call this, value or specifications. Okay, if you can still remember the kilo, the mega, which these are commonly used in resistors. But for pico, nano, and micro and millifarad, this is intended for capacitors. So for microfarad, we have 10, which is equivalent to 10 negative 6 farad, or nano. We have also the nanofarad or NF, which is equivalent 10 raised to negative 9 farad, and the pico, which is equivalent to 10 raised to negative 12 farad. So these are the different value for electrolytic and even other types of capacitor. Another component for capacitors is the mica. It's a one-of-a-kind capacitor wherein definitely the material based on its term is mica. It's a silicate mineral. It is instead of a gel or paste used in electrolytic. Mica as the mineral is the direct dielectric material that can be found in rocks, granites. These components are reliable, stable, and high precision, which is available from different regions like low to high voltage. The capacitance range is from 20 picofarad to 10 microfarad. It is applicable where low capacitance and high accuracy changes over time are required. So, mica is made up of metal foil plates, and the dielectric is, yeah, the mineral, which is the mica. So this is the illustration of what's inside a mica capacitor, and this is the actual picture of this component. So meaning to say, we can distinguish or differentiate capacitors based on the dielectric material, not just the shapes, the size, the corresponding voltage or application. Uh, we can easily determine through its material or the dielectric. Next component after mica is ceramic. It's also a well-known capacitor, and it is a fixed component, where the ceramic is the dielectric material. It is constructed of two or more alternating layers of ceramic and a metal layer that serves as the conductive plates or the electrode. Of different types of ceramic capacitors, the most prominent or commonly used is the MLCC. MLCC is the multi-layer ceramic chip capacitor, and the other one is the ceramic disc capacitor. So what is inside a ceramic? So this component has a protective coating For resistors, we call this insulating jacket or casing. Right. And what's inside is the electrode. And the dielectric for this component is no other than the ceramic disc. So we also have the hold off kink and the connecting wire for this passive component. And this is the actual picture of a ceramic capacitor, wherein you can see a three-digit symbol. As I've said again, we will discuss how to read capacitor and to know its corresponding value. What are the applications of a ceramic capacitors? These components are used in printed circuit boards, which are high density applications. It's an unpolarized component, makes it suitable for general applications. You can find this in DC motors as they are used for reducing the RF noise. When you say RF, this pertains to the radio frequency. Ceramic capacitors are also used in transmitter stations where resonance circuits are also used. The next component for capacitor is the film. Other term for this is the polymer film, plastic film, or film dielectric. So you can easily guess that the dielectric for this component is the film. The good thing about this component that they are inexpensive and they come with a limitless shelf life. It uses a thin dielectric material with the other side of the capacitor are metallized. The range or the voltage range of this component is from 50 volts to 2 kilovolts. So this is the actual picture of a film capacitor. So uh, mostly, if you're going to describe these components, there are like candies with various shapes and sizes. But these candy-like components are has wide array of applications. Or they're used for resonance circuits. They're used for uh, removing for filtering or removing radio frequency noise or other forms of ripples or disturbances. And aside from the storage capacity, also has a low to high voltage density applications. For this component, films are used as safety capacitors and in electromagnetic interference. These film capacitors find applications in power electronics. You can mostly find this in power electronic devices. These components are used for safeguarding the devices from sudden voltage spikes. Uh, they're also used for improving the power factor of the device. Another component is the paper, also known as fixed capacitor, wherein the dielectric material is the paper. The amount of electric charge stored by the paper capacitor is fixed. It consists of two metallic plates and paper as a dielectric material and is placed between these plates. Let us see what does a paper capacitor looks like. So this is the illustration of a paper capacitor, and this is the paper or the dielectric material. Okay, and these are the plates or wherein the dielectric material is in the middle of the two separate plates. So this is the an example of a paper capacitor. The applications for this component are used as safety capacitors also. Okay, so the next topic that we're since we know that the different types of capacitor, its meaning, its applications, and types. Let us now try to understand or study how to read the capacitor values. First, let us get to know how to read large capacitor. The first thing you're going to do is know the units of measurement. Since we already know that the unit of measure for capacitance is farad or capital F. So meaning to say, this value is much too large for ordinary circuits. So household capacitors are labeled with one of the following units. 1 microfarad or millifarad is equivalent to 1 microfarad, which is equals to 10 raised to 6 farads. Therefore, in other contexts, microfarad is the official abbreviation for millifarads or 10 raised to 3 farads. Some of you might confuse between the symbol like UF or MF. UF like symbol, it means micro. So 1 microfarad is different from 1 millifarad. Okay. Another is 1 NF is equivalent to 1 nanofarad is equals to 10 raised to 9 farad. So let's get to know the equivalent value for this farad or for this unit of capacitance. 1 pico is equivalent to 1 picofarad is equals to 1 farad. Okay, so that is the label or the units for capacitance. So here, in reading large capacitors, wait, okay, that is how we what do you call this? Look at the corresponding value. I think I showed this a while ago. Since we discussed about the the electrolytic capacitors, wherein microfarad is equivalent to 10 raised to negative 6 farad. Nano is for 10 raised to 9 farad. And picofarad is equivalent to 10 raised to negative 12 farad. Next is, in reading the value of the capacitance is um, what we call, um, yeah, it is how you read the capacitance value. Most large capacitors have a capacitance value written on the side. As you can see, based on the illustration, the symbol is the value for capacitance is written at the end or the other side. For example, we have 450 volts and 47 microfarad. So here, the below the electrolytic, we have this 102 or the M letter, which is equivalent to 1 nanofarad. This plus and minus 20%, this is also the tolerance, which can also be found in resistors. And FT is equivalent to farad. So this is for large capacitors. Again, if you see these letters or text or symbol, UF, it's like a the meaning of this is microfarad. If you got M letter at the end of the figures or numbers, that is equivalent to 1 nanofarad and a tolerance of plus or minus 20%. And for large capacitors, which we have FD, which is equivalent to farad. Slight variations are common, so look the value that most closely matches the units based on the illustration. These are the following you need to adjust. Ignore capital letters in the units. For example, MF is just a variation on F. It is definitely not a megafarad, even though this is the official unit of abbreviation. Another thing, class, don't get thrown by FT symbol or letter. This is just another abbreviation for farad. Okay? Beware again, beware also for single letter marking such as 475M. These are usually found on smaller capacitors. Okay. So next um, is look for tolerance value. As I mentioned a while ago, even capacitors has also its tolerance. So based on the picture, we have 50 UF or equivalent to 50 microfarad. So it has a tolerance of plus or minus 5%. In getting, if it's plus 5%, 50 microfarad plus uh, 50 micro times 0.05, you will get you will get 5.25 microfarad. This is the maximum tolerance for this component. While if it's negative 5%, its total our minimum tolerance is 4.75 microfarad. So that's how you compute for the maximum and minimum tolerance value of this component. So some capacitors list a tolerance or the maximum expected range in capacitance compared to its listed value. This isn't important in all circuits, but class, you may need to pay attention to this if you require a precise or exact capacitor value. For example, capacitor labeled 6,000 microfarad has a positive 50% or minus 70, could actually have a capacitance as high as 6,000 microfarad. Okay. If there is no percentage listed, look for a single better letter after the capacitance value or on its own line. This may be code for a tolerance value based on the succeeding slides. So let's get to know more about it. Let us check the voltage rating. If you see a text of let's say 103, it has a KB. So 1 KB is, as we know, is equivalent, kilo is equivalent to 1,000. Since we have the letter B, 1 KB is equivalent to 1,000 volts. Another thing is the letters. Okay. Look at the next component. PP33J has a 2A. 2E, I mean. The 2E pertains to 250 volts. And we also have BAC. So BAC is means AC circuit. So what's the meaning of this? These are what we call voltage rating. If there is a room on the body of the capacitor, the manufacturer usually lists voltage as a number followed by a B, as you can see, BDC, BDCW, or WB. Or meaning to say WB stands for working voltage. This is the maximum voltage the capacitor is designed to handle. So 1 kV is equivalent to 1,000 volts. Okay. If you are building an AC circuit, look for a capacitor rated specifically for BAC, which is equivalent to AC circuits. Do not use a DC capacitor unless you have an in-depth knowledge on how to convert the voltage rating and how to use that type of capacitor safely in AC application. Since we know the difference between a DC and an AC application. So next is the positive or negative sign. This is commonly for electrolytic capacitor. So we should be particular. We should be careful on how we're going to connect the components in a terminal or mount it in a PCB or breadboard. If you see one of the next of this next to a terminal, the capacitor is polarized. Make sure, class, to connect the capacitor's positive end to the positive side of the circuit, or the capacitor could eventually cause a short or even explode. So let's be careful. Let us first know the polarity of the component. Or else, if you neglect to connect it in a wrong placement, it can damage the capacitor or it might explode. If there is no positive, or you can orient the capacitor either this way. Some capacitors use a color bar, uh, usually in a ring shape or barrel shape type, to show polarity. Traditionally, this mark designates the negative end on an aluminum electrolytic capacitor, which are usually shaped like tin cans. On tantalum, electrolytic capacitors, they are very small. This marks or designates positive end. Okay. So that's how you determine the polarity of the component. In tantalum or electrolytic capacitors. So another method of uh, try to know the capacitor value is reading compact capacitor codes. So kindly look at the drawing or illustration. So we have 47 3J. So first, copy the first two digits. So you have 4, 7. So what you're going to do again for emphasis, write down the first two digits of the capacitance to know the value. This is for compact capacitor codes. Older capacitors are less predictable, but almost all modern use the EIA standard code when the capacitor is too small to write out the capacitance in full. So just imagine how are you going uh, to write the value of this component since it's very small. That's why based on the IA code or standard code, they use letters. Okay. To start, write down the first two digits, then decide what to do next based on your code. So if your code starts with exactly two digits followed by a letter, for example, 44M, the first two digits are the full capacitance code. So skip down the finding units or skip down to finding units. If one of the first two characters is a letter, skip down to letter systems. If the first three characters are all numbers, continue to the next step. To know what I am saying, let's proceed to the next slide. So here we have use the third digit. So just copy the first two digits and the third digit of this component serve as a multiplier. Same as what do you call this? Uh, um, for resistors. But here, if a capacitor has a three-digit unit or value, the third part is the multiplier. So here, 10 times 10 raised to 5 is equals to, just copy the 5 zeros or place it up, no, just multiply and you will get, let's say, 1, am I right? 1 million. Okay? I forgot. Another thing. So 478, so 47 times 0.01 is equals to 0.47. Okay? The three-digit capacitance code based on this illustration work as follows. If the third digit is 0 through 6, add that many zeros to the end of the number. For example, 453, 45 times 10 raised to 3 is equals to 45,000. If the third digit is 8, multiply by 0.01. Example, 278 is equivalent to 27 times 0.01, you will get 0.27. What if the third digit falls on 9? So what you should multiply it by 0.1. Example, 309 30 times zero point 0.1, you will have 3.0. Next is work or write down the first two digits of the capacitance. No, sorry for the error on my it should be it should not be write down the first two digits, but it should be um, work out the capacitance units from context. So meaning to say, the smallest capacitors made from ceramic, film, or tantalum use units of picofarad. Again, the smallest capacitors for this component that are that the dielectric material are ceramic, film, or tantalum use units of picofarads, which is equivalent to 10 raised to negative 12 farads. Larger capacitors such as cylindrical aluminum electrolyte type or the double layer type use units of microfarads, which is equivalent to 10 raised to 6 farads. So a capacitor um, may overrule by adding a unit after it. P for picofarad and for nanofarad or U for microfarad. However, class, if there is only one letter after the code, this is usually the tolerance, not the unit. P and N are uncommon tolerance codes, but they do exist. Another way of reading the capacitor is read the codes that contains letters. If your code includes a letter as one of the first two characters, these are the three possibilities. If the letter is an R, yes, based on the picture, you have there for R1, okay. For R1, replace it with a decimal point to get the capacitance in picofarad or PF. For example, 4R1 means a capacitance of 4.1 PF. I repeat, based on the example, we have P 4R1. So we have the letter R. Instead, you have to uh, replace it with a decimal. Okay? If the letters is P, N, or U, this tells you the units. We have the pico, the nano, or micro. Right? Replace this letter with a decimal point. For example, N61 means 0.61 nanofarad. And 5U2 meaning to say it's 5.2 microfarads. A code like, okay, let's focus on the example. A code like 1A 253 is actually class 2 codes. Okay? IA 253, these are 2 codes. Meaning to say, 1A tells you the voltage and 253 tells you the capacitance. Okay? I repeat, IA talks about the voltage and 253 tells you the capacitance. So this is how you read codes that contains letters. Next is reading the tolerance code on ceramic capacitors. So for this illustration, ceramic capacitors, which are usually tiny pancakes based on its description, with 2 pins or terminals. Typically, this lists the tolerance value as one letter immediately after the 3-digit capacitance value. Look at the illustration. As you can see, okay, let's proceed to the next slide. I forgot to shift or transfer the slide. So this is how you read the tolerance code on ceramic capacitors. As you can see, each letters has equivalent tolerance code. So we have E202M. Okay. So M and the other one is Z. So each letters, or if you've seen a ceramic capacitor with a letter after the numbers, then we're talking about the tolerance code. Based on example, M is equivalent to plus or minus 20%. The other ceramic component, which is the last letter is Z, is equivalent to plus 80% over negative 20%. This letter represents the tolerance of the capacitor, meaning how close the actual value of the capacitor can be expected to be indicated value of the capacitor. If precision is important in your circuit, translate this. Okay? B is equals to zero point 0.1 picofarad. Okay? As you can see. Next is reading the letter number. Okay, let's proceed to the next slide. Reading the letter number, letter tolerance value. So how are we going to read its capacitance or the value of this component? Many types of capacitors represent the tolerance with a more detailed three-symbol system. As you can see, based on the example, we have the Z to R. Okay. Interpret this as follows. The first symbol shows the minimum temperature. Z is equivalent to 10 degrees Celsius. Okay, 10 degrees Celsius. And the next digit is 2. What does it mean? 2 is equivalent to 45 degrees Celsius. While the other 4 is 65, 5 is 85, and so on. The third symbol shows variation in capacitance across this temperature range. This range from the most precise A is equals to plus or minus 1.0%. But to be specific, the given is R, 3 to R. So it's what do you call this? Its capacitance across the temperature range is plus or minus 15%. So that is uh how you read letter, number, letter, tolerance values. I hope you can follow, class. Okay, so this the other method of reading the capacitance values. We have the US military capacitor chart. If you can see the CM or DM, and just like also resistors, each the capacitor also has color bands or dots. So we can refer to color code. Okay. So we are done with the capacitors. What are its applications or function? Even the different types based on its schematic symbol and the actual values. Aside from that, we discuss also the different the different classifications of this component, starting from electrolytic, mica, ceramic, paper. So we can recognize the difference of these components based on its dielectric material. So another component that I'm going to introduce is the inductor. As I've said, we already encountered these components several times based on the lessons that I presented, activities that, or even the learning materials and videos posted in our classroom. So let's get to know more about inductor. Inductor class is also called a coil. Aside from coil, it could be a choke or a reactor. It is also a passive two-terminal component that stores energy, however, in a magnetic field when electric current flows through it. Battery, capacitor, these are components or even device. There is resemblance or similarities. They stores electric charge. Okay. However, battery is different from capacitor. Battery can produce and it's a source of electrical energy and it can store also or the storage of electrons. While in the case of capacitor, these are just storage, not producers of electrons. But in the case of conductor, it also stores energy in a form of a magnetic field when electricity or electric current pass through. So, how does an inductor look like? So, generally, it consists of an insulated wire wound or wrapped into or formed in a coil. If capacitance is measured in farads, if resistance is measured in ohms, inductance, the unit of inductance is measured in Henry or capital H. It's named based from a scientist, a 19th century American scientist in the name of Joseph Henry. So, what is inductor? How does it work? An inductor is a simple electronic component, or in other words, it's simply a coil of wire. Look at the picture. This is an inductor. It's a coil of wire. It turns out, however, that the coil of wire do some interesting things because of its magnetic properties. So from the definition, when electrons flow through this component, it forms a magnetic field. Okay. So what will happen to the bulb when electricity pass through an inductor? What you see here is a battery, a light bulb, a coil of wire around a piece of iron, yellow, and a switch. So this coil of wire is what we call inductor. If you already studied or understand how electromagnets work, you might recognize that the inductor is a example of electromagnet. If you were to take the inductor out of the circuit, what you would have is a normal flashlight. You close the switch and the bulb. You close the switch glass and the bulb lights up. With the inductor in the circuit as shown, the behavior is completely different. The light bulb is a resistor, the resistance that creates heat to make the filament in the bulb glow. The wire in the coil has much lower resistance. It's just a wire. So what you would expect when you turn on the switch is for the bulb to glow very dimly. Meaning to say, most of the current should follow the low resistance path through the loop. What happens, class, is that when you close the switch, the bulb burns brightly, and then it gets dimmer. When you open the switch, the bulb burns very brightly and then quickly goes out. The reason for this strange behavior is because of the inductor. When the current first starts flowing in the coil wants to build up a magnetic field. When the field is building, the coil inhibits the flow of current. Once the field once the once the field is built, current can flow normally through the wire. Okay? When the switch gets open, the magnetic field around the coil keeps current flowing in the coil until the field collapses. So this current keeps the bulb lit for a period of time, even though the switch is open. So in other words, class, an inductor can store energy in its magnetic field, and an inductor tends to resist any change in the amount of current flowing through it. So let us get to know more about the different types of inductor. So as you can see in the picture, it comes in a variety of shapes and sizes, and its coils, how it was wrapped around. So we have a cylindrical, and the other one is like a transformer. So don't you know that inductor are simply like a transformer? However, transformer has two coils, the primary and the secondary. So these are its types. We have the fixed, variable, we have the preset or the adjustable inductor. And this is the actual shape. So we have an air core type, iron core, and ferrite core. So these are the different types of inductor. Another interesting component in electricity and electronics is what we call a diode. Diode is a semiconductor device that essentially acts as a one-way switch for current. So this component allows the current to flow easily, but in only one direction or movement. It, it also restricts, just like resistor, the current from flowing in the opposite direction. Diodes are also known as rectifiers. If you can still remember, for the past videos or lessons that I discussed, wherein I mentioned there the role of diodes in a power supply. So, uh, uh, the IN407, based on the example, are what we call rectifier diodes because they change alternating current or AC into pulsating direct current or DC. Diodes also have polarity. So, we have the positive and negative. But in the context of diode, the positive lead is what we call anode and cathode is the negative. So this is the actual symbol of a diode. The positive, the anode, and the cathode. So this is the arrow direction and it has a bar. Okay? And these are the different schematic symbols. So they differ based on the bar. Okay? But they have a constant arrow. The only difference based on the illustration are the symbols and the direction. We have for the junction, Zener, tunnel, Schottky, Baractor, diode, triac, light emitting diode, photodiode. These are example of diodes. And these are the actual, what do you call this, component. Okay. So diode, what do you call this, allows current flow. Either when we say current flow, we have two types, forward and reverse bias. When a diode allows current to flow or to pass through, that is what we call class forward bias. But when a diode acts as an insulator and does not permit to current flow, that is what we call reverse bias. Yeah, it's strange but true. The diode symbol's arrow points against the direction of electron flow. Reason: engineers conceive the symbol and their schematic show current flowing from the positive side of the voltage source to the negative. It's the same convention used for semiconductors that includes arrows. So arrows pertains to direction. The arrow points in the permitted direction of conventional flow and against the permitted direction of electron flow. So that's how we differentiate a forward and reverse bias. So how to determine if we have a good or bad diode by means of testing? So based on the illustration, using a digital multi tester, we can determine or describe or interpret that we have a good or a bad diode. So what is the characteristic of a good diode and how can you observe it using a digital multi tester? Okay. A digital multimeter or multi-testers test diode produces a small voltage between the test leads. So by the way, here's uh, here's an example of a multi-tester. So this part is what we call the range selector, and this type class is a digital. Okay, and we have a LEDs or terminals or probes in some books or reference. The red signifies positive and the black is a negative or common terminal. Okay? So adjust first the range to a diode symbol in testing this component. Normal voltage drop is 0.5 volts to 0.8 volts. The forward bias resistance of a good diode should range from 1000 ohms to 10 ohms. When a reverse bias, a digital multimeter's display will read OL or point which indicates very high resistance. Okay? Diodes are assigned current ratings. If the ratings is exceeded and the diode fails, it may short and either allow a current to flow in both directions or B, have the current from flowing in either direction. Okay? I repeat, diodes are assigned current ratings. If the ratings is exceeded and the diode fails, it may short in either allow current to flow in both directions, since that is not a description of a good diode. Half of the current from flowing in either direction. So based from the illustration, not this one, this is a good diode. Um, this is a bad diode because the flow of current is it allows the flow of current in both directions. So a good diode should allow the current to flow in only one, not in both directions, or half of the current from flowing in either direction. So look at the difference. Okay, it should have uh, it should produces a small voltage for a good diode between the test leads enough to forward bias a diode junction. It should be zero point 0.5 based on its voltage drop, zero point 0.5 to zero point 0.8 volts. Okay. If you're using a digital multimeter, a good diode should display OL, which indicates very high resistance. Okay. If 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 the rating exceeded and the diode fails, that will become a bad diode because it will allow the current to flow in both directions or half of the current from flowing either directions. Okay, so these are the bad diode results when testing using a digital multimeter or tester. Another component that we need to know, I will just, since we have limited time, I'll just provide you the essence or a brief overview about this component. So transistors are semiconductors, a miniature semiconductor that regulates or controls the current or voltage flow. In addition, apply amplifying, when you say amplify, to strengthen, and generating these electric signals and act as a switch or gate for them. So transistor can be described if it is an amplifier. If when working as an amplifier, a transistor transforms a small input current into a bigger output current. But if a transistor acts as a switch, it can be in one of two distinct states. As I've said, on or off, this is the binary operation to control the flow of electronic signals through an electrical circuit or electronic device. So transistor is the foundation of digital electronics. What are the benefits or application of this component? First, it provides a signal amplification or strengthening to ensure a pair output for the application. Second, it regulates an incoming signals for current and voltage. It serves as a regulator. Compared to vacuum tubes, are going to trace its history as what I presented for several meetings. Transistors are smaller and lighter. And even though they are smaller, they are mechanically stronger. Aside from that, they require no external heating for operation. Unlike vacuum tubes, I mean. It has a low voltage supply sufficient to operate a transistor and highly suitable for low power applications. Another benefit or advantage, it is ideal for integrating with resistors and diodes to create IC or integrated circuit. And based on its size, transistors decrease exponentially, their cost has fallen. So this is cost effective compared to other components because of its size. So these are the transistor types. We have the BJT or bipolar junction, and the field effect transistor. So as you can see, uh, transistor can be classified into bipolar junction type or the field effect transistor. Under BGT, we have NPN or PNP type. The negative, positive, negative, or the PNP, the positive, negative, positive. So field effect can be classified into two types: the junction FET or the metal oxide or the MOSFET, semiconductor field effect transistor. So that's how we have a variety of transistors, just like other components. So this is the actual transistors with a corresponding value. Right? So that is how I end my presentation about an introduction in even a small span of time, since we only have 2 meetings. Hopefully you learn another information or knowledge about an introduction to various components used in electricity and electronics. That's all class for today. Thank you for listening. Or if you have questions or classification or questions, I'm sorry, if you have questions or clarifications, feel free to message me based on the contact details. So class, I hope you enjoyed this lesson or this video. Uh, I decided to record this material so that you can continue working on your project. Uh, Perhaps, or should I say, we will conduct a sync meeting on Friday, since that will be our last meeting to discuss or to give me an update or status of your project. And the reason why I decided to record this material so that you can also give time to comply all the requirements. Again, take a second look, go back, or try to visit our Google Classroom and make sure that you already answer or accomplish the learning tasks, activities, quiz if we have, even the laboratory experiments. Since this course is divided into two, we have lectures and laboratory. So class, if you have questions or clarifications again for emphasis, try to contact me based on my contact details. So in order for me to address your concerns. So thank you for listening. Thank you for your time watching this video. And as what I always say, keep safe always.
Zombie apocalypse.